Hello, this is the second part of the lesson on torsion in circular sections. We're going to start with the angle of twist in a shaft. Similar to what we talked about in the last lesson about strain. You get elastic deformation due to torsion in shafts. So a shaft of length L, when subject to a torsional load, will deflect. This deflection is known as angle of twist. Again, this is elastic deformation. It will revert back to its original form when the couple or the torque is removed. I'm going to leave this up to you to go derive this equation, 12.6 in the textbook. But essentially where it comes from is the formula for stress and then strain. It's very similar to our delta equation that we derived in the last lesson. So theta is the angle of twist. Now the units for angle of twist are going to be in radians. We like radians because it's dimensionless, kind of like when we talked about axial deformation. We talked about it strain in terms of a dimensionless parameter, inches per inch. Okay, so radians here is a dimensionless parameter. You can convert radians to degrees, where 1 radian equals 57.3 degrees. So essentially 2 pi radians equal 360 degrees. That's how you get 57.3 degrees. T is the torque. We're going to use pound inches or Newton meters. L is the length of the shaft that's subjected to the torque. J again is the polar moment of inertia, and then G is the modulus of rigidity. Okay, so this is a elastic deformation equation, and so we're using the modulus of rigidity. Equation 12.6 is applicable for solid and hollow circular shafts. The difference between the two is how you go about calculating J. And then again, J, the formulas for the polar moment of inertia, J, are in the back cover of your textbook. Transmission of power. In a lot of engineering problems, rotating shafts are used to transmit power in machinery. So work is done by applying a torque to turn the shaft. In linear motion, work equals force times distance. Okay, so but in a rotating motion, work equals torque times angular distance. It's analogous to the work equals force times distance, except we're talking about torsional work. And in this case, theta again is in radians, the dimensionless parameter. Power is the rate of doing work. Therefore, we can relate power and applied torque in a rotating shaft. Okay, so if we look at shear stress in a shaft, it's always in terms of torque. Okay, and if we look at the angle of twist in a shaft, the equation for it is in terms of torque as well. Okay, so now when we look at rotating machinery, we can start relating the horsepower being transmitted by a shaft into torque, and then we can start calculating what the stress and angle of twists is for a shaft that's used to transmit power. So this equation, again, you take a look at your textbook for how it's derived, but equation 12.7 in US units is the horsepower that's transmitted by a shaft is related to torque times the speed of the shaft, and this speed is in the number of revolutions per minute, or RPM. And then T is in pound inches, and then HP is in horsepower. And then we have this constant 63,025. In the next slide, I'm going to derive that constant for you. So we know that 1 horsepower equals 550 pound-foot per second, and we also know that 1 revolution equals 2 pi radians. So I'm going to start with equation 12.7. I have torque in pound inches times speed of the shaft in revs per minute. Okay, so we're going to get that into dimensionless quantity of radians, and we know that there are 2 pi radians per revolution. Then I'm going to convert my inches into feet. So for every foot, there's 12 inches. I'm going to convert my minutes into seconds. That takes care of my minute units. And then horsepower is actually 1 horsepower equals 550 foot-pounds per second. So this is like multiplying the equation by 1. If you look, all the units divide out. Pounds in the numerator, pounds in the denominator, inches in the numerator, inches in the denominator, revolutions in the numerator, revolutions in the denominator, minutes, minutes in the denominator, numerator, feet, numerator and denominator, and then seconds here, seconds and seconds. So all we're left with is units of horsepower. And if you take all of these constants in here and multiply them together, you get 63,025. So for equation 12.7 in the international units, the units of power is a watt. And a watt is essentially 1 Newton meter per second. So in this equation, we're using, again, revolutions per minute in this equation, and then the 60 comes from converting the revolutions per minute into revolutions per second as required for watts, and the 2 pi in this equation is used to convert our revolutions into radians. So it's a little bit simpler units to work with.